Okay, so next we are on the energy conservation equation, and if you are crossing any terms out, you need to explain why. Again, I usually write them next to the arrows, but you can also write them as step 2 in more detail. So here we crossed out delta I and Q, and delta I is the internal energy. So it depends on the molecular level changes, and that happens if temperature or pressure is changing. So we are saying there is no temperature or pressure change, so delta I is taken to 0. And there's also no heat transfer. It's not added, not taken out of the system. So Q is 0 for that reason. So that's the first simplification. Next step, step 3, is drawing a free body diagram as we gave it to you earlier. That's the step. So for this one, since we are doing it from 1 to 2, I need to take this free body diagram. I need to draw this free body diagram between these two. I usually don't do it at point 1 or point 2. I do it somewhere in between. So to make sure that I consider all the forces that I may have. Okay, somewhere in between. Since spring is not going to be relaxed, so if you take point 2, spring is relaxed and you don't have the spring force. But you cannot assume that because you're doing the energy conservation from 1 to 2, not just for point 2. Okay, that's why it's safer to take in between. So we have this spring force. Again, since x was up the incline, spring force is down the incline. It's pushing the object down, basically. And weight force has 2 components, right? And the normal force is also perpendicular to the surface. So if you kind of take it like this, x and y. The thing is, this is not a Newton's second law problem, okay? The free body diagram is needed to see all the forces acting on the object so that we can split our total work term into pieces. So there should be 3 pieces, one for weight force, one for normal force, and one for spring force. If it was chapter 7 problem, we would probably figure out the work done by those forces rather than keeping them as energy, okay? So let's just investigate each of them, but chapter 8 is more potential energy for now, and then later on other energies as well. So if the force can be associated to the potential energy, that's what we are going to prefer doing it, because work term, finding work, is a little bit more involved. It has dot product, it requires vectors, but energy is simply either mgh if it is gravitational potential energy, or 1/2 kx squared if it is elastic potential energy. So they are much easy to deal with. They are a scalar. Work is also scalar, but it comes from the dot product of between 2 vectors, so that's why it's a little bit more involved. Okay, so from now on, when I solve problems, if I can associate them to the energy, I will do that instead of finding the work done. And unless I'm asked to find the work done by a specific force, that's what I'm gonna do, basically. Okay, so 3 terms, work done by the weight force. Again, we are going to count that as gravitational potential. There is a change in elevation, so there is work done by the weight force. But in the energy conservation, we are going to ignore it because we're keeping it as delta UG, okay? And the normal force doesn't do work because the displacement is going to be down the incline, and normal force and the displacement, as you can see, they're perpendicular to each other. So the angle cosine theta, theta becomes 90, cosine 90 becomes 0. So that is simply 0. That's why. But we are not associating it with any energy, okay? And the spring force is another conservative force as a weight force, as we discussed that earlier. And there are notes regarding that. So if you don't remember that, please double check that. It's kind of an important concept right now. So since it can be associated with the elastic potential energy, we are going to keep it as that in the energy conservation equation. And that means we don't have any work terms to show here. Okay, this means this is the work in the energy conservation, okay, equation. That's why you plug it in for the total work. It doesn't mean that there is no total work in the system. If they're separately asking you to find that, then you have to find out what the work done by the weight force and the work done by the spring force. But this simply means, again, on the right side, we have 0. Okay, the work goes to 0. So we kind of eliminated that. Okay, I hope that is clear. And if you have any questions with that, let me know later. Okay, so once you simplify the equation, there are 3 energy terms, and there's nothing left on the right side. Next step is kind of simplify, so expand those first and then simplify. Delta means final minus initial, and remember 0.2 is final, 0.1 is initial, so it's going to be 2 minus 1 for each energy term, and that's what we are how we are expanding the terms. Be careful with the signs. The initial ones are going to have negative because change is final minus initial. That's why we have it in this form. So again, this is our delta K, and this is delta UG, and this is delta UE, okay? Final minus initials. Next, simplify them. Initially, the speed was 0, so since K is 1/2 mv squared, that goes to 0. And final, at 0.2, the gravitational potential is going to be 0 because remember for part A, we took that point as our origin, so the y is equal to 0, that is y2. And for the elastic potential case, at 0.2, spring is at the relaxed position, so there's no more spring force on it, and that means the elastic potential energy is 0. Okay, x2 is 0, 1/2 k x2 squared becomes 0. And next we have 3 terms left, and we're just going to write down. So first is K2, 1/2 mv squared 2. UG1 has a negative sign, so be careful with that. We're keeping that sign here. It is mgy1. And again, since this is initial elastic potential, there's also a negative sign, and that is 1/2 k x1 squared. Okay, and rearranging this equation for V2 should give you this. So first we are, let me show that algebra quick. Let's multiply everything by 2. So these 2's are going to go away, right? And you have 2 mgy1, as you can see. You can put it on the other side. It becomes positive because it was negative. And then you put this, so we put that term there. And then when you put this term there, you get positive k1x squared. And divide both sides by m because that's the coefficient of v squared, and that's why we have divide by m. And since it was square, you are taking the square root, and that's what we have. So this is our equation. Again, try not to plug in any numbers, and you'll see you can catch your mistake that way better, because sometimes you will mess up with the signs and such. Okay, so next is to find V2. It looks like we need to figure out the relation between x1 and y1, okay? But they are related. Again, this tilted surfaces, energy problems, this is a very common thing to do, okay? So here's the triangle we have for that. So if we go back to here, I'm going to go back to the original problem. So it is like this triangle here, okay? This is y1, since y2 is 0. So we are relating that x, so this was x1 as well. We are relating those two, okay, in that triangle, and it's right here. Again, the vertical is simply y1, and the hypo is x2. So this is opposite of this angle, divided by the hypo. And that gives us sine 37. To solve for y1, we plug the others one in, and we have the answer. So another way of writing that, y1 is simply x1 times sine 37. Okay. Now we are going to plug the numbers in here again. Make sure to check the units as well. Newtons is kilogram meters per second square. So we're going to kind of get rid of those kilograms with this kilogram in here at the bottom, and you get then meters squared per second squared. When you take the square root, the answer should be in meters per second, as the units are also worked out here, and taking the square root gives us 2.40 meters per second. Okay, so that is how we find the speed of the object when it is passing through the relaxed position. We call that 0.2. And I'm going to explain next part in a separate video.